All right, so we're going to have a little conversation now about what we call STP. STP stands for standard temperature and pressure. Now, this phrase, standard temperature and pressure, bothers me a little bit. It bothers me because, well, I think it's a little misleading. Standard means like normal, generally. You can also think of it as standard in terms of a standard that somebody has set to compare against other things. And that's what we're talking about here when we say standard temperature and pressure. Because standard temperature and pressure is pressure at 1 atmosphere, which is the kind of pressure you would feel when you're standing at sea level, right? 1 atmosphere. But which you would say, oh, that's general normal pressures. That's what you feel when you're in the lab, right? Unless you're going to school at Colorado, it's the normal pressures of the world, right? So that's normal. But when we talk about the temperature of STP, it's at 273 Kelvin. Is that an average temperature, Landon? Do you know what the Celsius temperature for 273 Kelvin is, Landon? If my temperature is 273 Kelvin.
To the opposite and subtract T.
That's right. So what would our Celsius be then? So, Robert, any ideas?
0.
That's right. 0 degrees Celsius. 0 degrees Celsius. So to go from Kelvin to Celsius, you subtract that 273, right? So standard, isn't 0 degrees Celsius isn't a normal temperature. It's not a bad standard, right? In terms of freezing point of water, sure, that's fine. But it's not a normal everyday temperature that we interact with. So there's always conversations about the volume of 1 mole of gas at standard temperature and pressure. And it's very useful. It's important to understand. It's important to recognize. But the problem is sometimes people forget what standard means in the standard temperature and pressure. People start thinking standard temperature, oh, that's room temperature. Standard pressure, that's atmospheric pressure at sea level, 1 atmosphere. But standard temperature is not standard meaning everyday temperature. It's standard meaning the temperature at which water freezes. All right? But with our PV equals nRT, PV equals nRT, we can solve the volume for 1 mole of gas at 273 Kelvin, mole of gas, 1, pressure, 1 atmosphere. All right. Our volume is what we're after. Who's up there? Is that Chad? Chad, you want to finish this up for us? What will the resulting volume be for this 1 mole of gas at STP?
First time is 22.4.
22.4. That's the fairy tale or the legend. Let's see if it's right. Okay? So let's put it into our math here. We got R. What was our R, Chad? 821. So 0.0821 times our 273 divided by 1. 0.0821. Did I get it wrong? What did I do wrong? There we go. 0.0821 times 273. There we go. All right. So it's true. 22.4. 22.4 liters. That's a pretty big balloon, right? How big is 22.4 liters? Here's me, fine outstanding citizen, normal person, a 22.4 liter balloon. What do you think? About that big? Maybe a little bit smaller? But it's a fair size, right? 22.4 liters. So if I had 1 mole of water, does anybody know how much volume 1 mole of water would be? Taiwan, what's the volume of 1 mole of water? Let's write down that question for ourselves. What do you think, Taiwan? What is the volume of 1 mole of water? Any ideas, Taiwan? Harry, why don't you help us out? What's the volume of 1 mole?
Sorry, can you learn this?
Well, we've never talked about it like this, but we do know how to do this, right? How about this? What's the mass of 1 mole of water?
Let's see. 18 grams.
That's right. 18 grams for every mole, right? And if I want to go to volume,
Okay.
let's say I want it in milliliters, that's a volume. What could I use? What conversion factor could I use? What do I need to have down here, Harry? What do I want to get rid of?
The grams.
Grams. And what do I want? Milliliters, right? Yeah, so what do we call that? What is that? That's the density.
Yeah.
Per milliliter. What is the density for water? Remember the density of water? It's 1 gram is 1 milliliter. Okay? So I find out that there's 18 milliliters for every mole of water. 18 milliliters. Okay? So how large is 18 milliliters? Maybe a box like that, right? I mean, just something smaller than the size of your fist, right? And I converted it to a gas. If all the material in that water was converted to a gas, its volume would expand, again, 22.4 liters if it was at 0 degrees Celsius. It would be larger at something like 100 degrees Celsius, much larger than that, right? So what we see is that you take a small amount of a substance, but in the gaseous phase is going to take up a relatively large volume. Okay? Now, notice this. The question says calculate the volume of 1 mole of, what kind of gas did it say here? Precious? Did it say it was gaseous water? Did it say helium, hydrogen?
I'm not really sure.
It doesn't say, right? It doesn't tell us. It doesn't tell us what kind of gas. And the reason it doesn't tell us what kind of gas is because it doesn't matter. It doesn't matter. Now, this is kind of new to us in terms of thinking about volumes of material, right? If I draw a water molecule, there it is, H2O, right? And say, okay, you know, that's how big it is. And then I draw a different compound. Maybe I draw something like octane, right? 1, 2, 3, 4, 5, 6, 7, 8. 8 carbons, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18 hydrogens. All of these are hydrogens. Okay? Here they all are. Much larger compound takes up much more volume than this compound here. But if I have a balloon of water or a balloon of octane gas, let's say, as long as they're both a gas at the same temperature, the same pressure, and as long as I have the same moles of material, the volume of the balloons will be the same. It doesn't matter the size of the compound that is in the gaseous phase. And that's because these things are gaseous and zooming around and colliding with each other only relatively infrequently, right? They're moving around. They're not being held together and compacted together. So the space that they take up is only dependent on their temperature, right? Whatever the pressure is, the volume of the system that you provide, right? These are the parameters that determine what the volume or the characteristics of the gas are. It doesn't have to do with the molar mass of the material. Okay? Very good. Okay, so here are some other problems using perv-nert, which I think we can practice on Friday a little bit more, specifically with some questions. We're going to talk about an idea of situations where we have more than one gas in a condition or in a container or in the atmosphere where we're looking at. If you have more than one component in your gas, the resulting pressure of the individual components of the gas is related directly to the moles of those different gases in the total. All right. So if we had an example like this where we have 520 millimeters worth of mercury, that's 520 torrs, of one gas into a cylinder, and then 250 millimeters of mercury of another gas into a cylinder, the overall pressure of this mixture would be just the sum of those two individual gases. The pressure contributed by the individual gases will be the sum of the two. So, Sarah, what do you think? What would be the resulting pressure in this container if I pumped these gases in at these pressures? That's right. I would just add up the pressure contributed by the the nitrogen, the pressure contributed by the oxygen, and that would be the total pressure in the system. Okay? So pressures of, like if I have a balloon here that I blew up with air, all right? I'm using air. I have my balloon still. Here it is. There it is. I got it. The pressure of this balloon, right? Whatever's inside this balloon. What is inside this balloon? Any ideas, Brielle? What's in here? What did I just put in there? Very good. What are the components of air? What's the major component of air? Nitrogen. That's right. This is about 80% nitrogen. And what's the second component? What did we say?
Oxygen.
Very good. 80% nitrogen, 20% oxygen, a little bit of carbon dioxide. But thank goodness for, when we breathe out, we don't just breathe out carbon dioxide. If we just breathed out carbon dioxide, then the whole CPR thing would be a fake, right? No, when we breathe out, we're essentially breathing out 80% nitrogen, 20% oxygen, a little higher concentration of carbon dioxide, but not much, not much. Okay, there we go. So the pressure in here, if I knew the overall pressure, I could know the partial pressure due to the nitrogen and the partial pressure due to the oxygen. For example, if I said I have 1 atmosphere of pressure in this balloon, that would mean I have 0.8 atmospheres from the nitrogen and 0.2 atmospheres from the oxygen. All right, and we would call these partial pressures because it's the pressure contributed by the different components in the balloon. All right. Another helpful tool in kind of thinking about the contribution of the different components is what we call the mole fraction of a material. So for example, if I know the total moles of, in this balloon here, nitrogen and oxygen, if I knew the total moles of nitrogen and oxygen in here, and I knew that it was 80% nitrogen, I could say that my mole fraction is, now fractions aren't represented in percentages, they're represented in just a fraction of 1. The mole fraction here, represented usually as this x, the x of nitrogen gas in my balloon would be 0.8, because instead of talking about it in terms of out of 100, this is out of a single 1. 0.8 fractions of all the moles of gas here are nitrogen. All right, Jace, then what would be my mole fraction for oxygen in this balloon? What do you think, Jace? What would be the mole fraction of oxygen in this balloon?
Just 8.2.
That's right. So we can talk about it in terms of percentage of the gas or mole fraction, because as we've identified, the volume of a gas is directly related to the moles of material when we're in the gaseous phase. Right? Let's do a quick review on that subject that we just said, that the volume of the moles of gas are directly related to the moles of the gas because they're in a gaseous phase. So for example, here's chemical reaction, X reacting with Y and forming X2Y. Okay, here it is. There's my chemical reaction. All right. If I react 4 liters of X with 2 liters of Y, how many liters of my product am I going to get? Okay, X2Y, how many liters of my product, my X2Y, am I going to get? Chad, is it your, no, it's Landon's turn. Landon. Here's my chemical reaction. I'll zoom in here a little bit for us. 2 X's combining with 1 Y, yielding this material. If I react 4 liters of X with 2 liters of Y, how many liters of product am I going to get? Any ideas, Landon?
Hang on one sec, I'm just writing down.
Everybody can kind of be thinking about this one. This is a little bit of a review from last class as well. If I react 4 liters of X with 2 liters of Y, how many liters of my product am I going to get? You want someone else to give you help, Landon, or do you think you got it?
Yeah, if someone else has it, they can go ahead.
Robert, any ideas?
I'm not 100% sure on this one.
How about this, Robert? What if I had said, if I react 4 moles of X with 2 moles of Y, could you give me the answer then?
Also, we're going to have to use the ideal gas law, the PVT.
Let's learn this. Very important here. 2x, gaseous phase, 1y, gaseous phase, going to x2y, gaseous phase. Here's the first one. If x, 2 moles of y, moles of x2y. With 4 moles of X with 2 moles of Y, how many moles of my product am I going to get? What'd you see? What'd you say, Robert? Or did you have it?
Yes.
4 moles of this material? Is that what you said?
Correct, because I mean, my reason behind thinking that is that when you're using up to the moles of the X, which makes it because I'm not sure if this is a reactive problem, but in the event that it would be, so that is a negative 4 moles total of the XY.
Okay. So if I have 2 X's, how many moles of Y do I need?
So that would be a total of 8 moles for there, so that would be 4. We need 4 for the 1.
2 moles of X. I just need 1 mole of Y, right? Can you see that? That's what my stoichiometry is showing here. X2Y. Can you see that okay?
Actually, is that what the 4 moles of X and the 2 moles? Oh, yeah. Okay, because okay, so it's because the moles of the X is 2 moles of Y, that's why it's a 2-to-1 ratio.
That's right. It's 2 to 1 here. 2 moles of Y. So, Chad, if I say, if I react 4 liters of X with 2 liters of Y, how many liters of X2Y am I going to get? Any ideas, Chad?
It's like really simple what we do at the same time.
Okay.
Why is many reactive forms? I'm guessing 2.
Okay.
Unless it's 8.
All right. So it sounds like Jace has, and Landon might have some ideas. Jace, tell us what you're thinking.
So, yes, you have 4 liters of X and then 2 liters of Y, and it requires a 2-to-1 ratio. So when you expand, so if you just do it, it's almost so simple as just doing 4 divided by 2, like the liters divided by the amount, so just 4 divided by 2 is 2, and then 2 divided by moles, which is 2 again, so it's just 2. So that's what I was thinking.
Now, that makes sense with last semester if you're talking about moles of material, but why can't you all of a sudden do that with liters of material too, Jace?
I
something kind of like that. Anybody else want to try to get a crack at it? Why don't you say yes in the screen or the chat down there if you want to try to talk to us about it. Harry, you got some ideas? Why don't you tell us? Okay, so what does that mean, Harry? When they're in the gaseous state, then what? So Harry says when they're in the gaseous state.
I think the concepts just say it.
Yeah.
When they're in the gaseous states, you can consider the molar ratios the same as the volume ratios.
That's right. Because, like we said, in gaseous conditions, N is moles of gas related to volume directly. As the moles increase, the volume will increase directly. So this statement here of this many moles of this material, 1 mole of that material, yielding 1 mole of this material, can also be stated in terms of volume. 2 volume units of X plus 1 volume unit of Y will yield 1 volume unit of this product here, only because they're in the gaseous state. Okay? Very good. So the answer is, just like this was 2 moles, if I have 4 moles of X with 2 moles of Y, I get 2 moles here. 4 liters of X and 2 liters of Y will give me 2 liters of my product. Okay, very good. All right.